All right, for our final project, we've created a robot that's capable of moving around on its own and, more significantly, detecting cliffs and moving away from them to avoid them. The way it accomplishes this is through an inertial measurement unit on the MSP430, which uses an accelerometer and gyroscope to monitor the position of the robot. So, the idea is we have the robot just move around arbitrarily until we reach an edge, which we can detect through a change in rotation. What we do then is have the robot simply back away from the edge until the accelerometer stabilizes, and then simply have it turn around and move in a separate direction, and then repeat the process. Now Victor is going to talk about the schematic.
Hello there. Yeah, so as you can see, I have the schematic for our final design up on the screen. And I think probably the most important thing right off the bat you're going to notice is that this MSP430 is a lot bigger than the normal ones we've been working with. That's because this one has the capability for 4 different PWM channels. And this is really important because we have 2 motors here and here that are driven by an H bridge. And each one can take 2 different inputs. So see, we have A1, A2, and B1, B2. This is really important because that allows us to control both the speed and the direction of the movement of our motors, which gives us greater flexibility. As Matthew had mentioned, we have a IMU, as we can see right here. There are plenty of different pins, including one that can trigger an interrupt. But it's very important in terms of all the capabilities, and the registers are storing the gyroscopic and accelerometer data in here. We also have some of our remnants of our old project right here, which are PIR sensors. So as we've talked about, we're using the cliff driving edge detecting robot. All right, so now let's go and look at some of the code. Ooh.
All right, so we have interrupts with our watchdog timer, and that is just to keep a counter just to see how long the motor has been running.
Okay, so the way we drive the motors is through pulse trains using PWM signals. So the idea is each motor takes in 2 signals, as Victor said earlier. One of them is going to be asserted and the other is going to be 0. Which signal is asserted determines the direction that the wheel is going to turn in, forward or backward, and the duty cycle of the pulse train is going to determine the speed. What this allows us to do is manually set the direction and speed that the robot moves in. So for instance, using this, we can decide to have both wheels moving forward to make the robot move forward. We can have one wheel go forward and one go back to have the robot turn in a direction. And we can use the speed to make sure that the robot is moving back with enough force to get it away from the edge, or moving slow enough forward to give it enough time to react to approaching the cliff. And the main component here that lets this work is the IMU, the inertial measurement unit.
And the inertial measurement unit communicates with the MSP430 through SPI communication. And the way that works is the MSP430 acts as the master and the IMU acts as the slave, and they're sending data back and forth to each other. And the IMU has a lot of different registers. Some of them they have a register for each axis from the gyroscope measurements and the accelerometer measurements. So if we want to read one axis of the gyroscope, we'd have to make a read register call, which would cause the chip select. The SPI communicates through this chip select, which signals the transmission is starting or ending. So we signal chip select low to say transmission starting. We would read the register from that one axis, and then we would signal chip select high once the reading is done and the buffer has been received. And we would do the same thing for the accelerometer. And that's about it for the IMU.
Okay, so we put this all together with a finite state machine. What we have the robot do on startup is it starts off by moving rather fast, just to give the motor enough strength to overcome the robot's inertia, just to get the wheels moving. Then we slow it down so it has enough time to react to an approaching edge. And so that's sort of its main state. When it approaches the edge, i.e. when the gyroscope and accelerometer detect the rotation, we have it move back quickly in order to once again give the wheels enough power to get it away from the edge so it doesn't pitch over while it's currently rotated. Since if we do it slowly, then it gives it more time for its inertia to pitch downward. Then we have it once again slowed down, since if the robot's moving too fast in this direction and we try and suddenly change its direction, it'll end up jumping up a bit, which can affect the efficacy of the IMU, or in a worst case scenario, just cause the robot to flip over. And then we have the robot turn in a direction which is decided randomly and continue back to the main state where it's gonna continue trying to move forward until it encounters another edge.
That's our video. I hope you like it. If you want to see our robot in action, definitely check out our demo. See you next time.
Bye.